Okay, let's talk a little bit more about radioactive decay, and more specifically about what we call the half-life of a radioactive element. So first, what is half-life? And half-life is really what it sounds like. It's how long half of the unstable nuclei in a sample will last before they decay. More specifically, it's the amount of time for 1/2 of a sample, for 1/2 of a radioactive sample, a radioactive sample to decay. So let's say you have 100 grams of a radioactive material, and after 5 hours you have 50 grams of that radioactive material and 50 grams of its daughter nucleus. Then the half-life of that particular material would be 5 hours. And the half-life, an important point about this is that the half-life is independent. Okay, independent of sample size. Okay, independent of sample size. That's very important, because what that means is that if we go back to our previous example here, if I started out with 1,000 grams of that particular radioactive element, after 5 hours I would still have half of it left. So if I started with 1,000 grams, after 5 hours I'd have 500 grams of it left. Then after another 5 hours I'd have 250. Then after another 5 hours I'd have 125, and so on and so forth. So I'm talking about the half-life. It doesn't matter how much we start with, it doesn't matter how much we have left. After that period of time you're going to have another half of it gone. It's because it's a random process. Decay is a completely random process. You can't look at a sample of 1,000 or 500 or even 2 atoms of a radioactive sample and tell with any degree of reliability which ones will decay next, because it's a completely random process. Even if you're down to 2 atoms, there's still only a 50-50 chance of one of them decaying over the other. And so you can't say, okay, this one's going to decay, then this one, then this one, then this one. All we know is that it's going to occur at a specific rate, and that's what we call our half-life. Now, because of this, it ends up being an exponential relationship. And so if we were to graph the amount of, in this case we have sodium-24. Okay, so we start out, if we look at our graph a little more closely, we start out with 400 grams of sodium-24 up here. Now, if we follow our graph down, half of 400 is 200, so we go down to 200. Here's half of our initial sample. We come across, and there's our 200 grams of sodium-24. We come straight down, and we'll imagine that that's a straight line, and it intersects the x-axis at about 15. And so after 15 hours, there are 200 grams still left of an original 400 gram sample. So the half-life is going to be 15 hours. And now, what we should then see is after another 15 hours, we should have half of 200, which would be 100. So if we come down to 100, and we come across, here's our little x, we come down, and sure enough, after 30 hours, after 2 half-lives, we have half and half, so we have 1/4 of the original sample. After another half-life, we're down to 50. So after 3 half-lives, we're down to 1/8. And then after 4 half-lives, we're down to 25, so on and so on. So, half-life, random, exponential process. If we know how much we start with, we're going to know how much we end with after a certain amount of time, but we can't specify which individual atoms we have because it's random. If we're given a graph of the amount of a sample over time, from that graph we can calculate the half-life based on where those points of half of that material being left are. And if we know a certain number of half-lives have occurred, we can calculate how much of a sample we should have left.